Alright, so welcome to this DC circuit video. Okay, so of course before I start this video, let's do a very quick recap on our COE. So in COE we learned a few terminology. So first of all, of course, is our current. So what is current? Current is just the rate of flow of charges. So for example, let's just say you have a proton or an electron. Okay, anything that has charges, right? As an electric charge is known as charges, can be positive or negative. So we know that for positive charge you move, or electron you move, means that it's known as the charges. Okay, so in current, right, we know that there's two types of current. So first is your conventional current. So what is conventional current? Conventional current means you have a battery, then after that you have a light bulb, right? So after that you have a current coming out of the positive terminal of the battery. So this is known as your conventional current. Of course, we have another type of current, which is the thing that is actually flowing in real life, which is known as the electron flow. Okay, so yeah, so we need to know these two types of current. All right. Okay, so the very first formula in COE that we learn is Q_it. Q equal to IT. Q is what? Q is your charges, I is your current, and T is your time. So just remember, for physics, right, we always use the SI unit. For example, right, Q is your charge, which is in terms of coulomb. Then I is in terms of ampere, and of course T is in terms of second, not minutes, not hours, and not days. Alright, seconds. Okay, the second one will be your potential difference. Potential difference refers to anything but the battery. So for example, I can say, potential difference across light bulb or resistor. So what is potential difference? Potential difference is the amount of electrical energy converted to non-electrical energy when one coulomb of charge, right, passes through from one point to the other. Alright, so of course there's another formula that we learn in COE, which is okay, maybe you can just help me cancel V, help me put P, T. So potential difference is equal to W divided by Q. So what is the W here? W is the work done. Alright, so W is equal to work done. So of course, work done is the energy change. Every time we are required to find work done, we always see, what is the energy change? So in this particular case, is from electrical energy to non-electrical energy. Alright, so for the example of bulb, what is the energy change in the light bulb, which is electrical energy to light and heat energy. So that is the meaning of work done in this particular case. And of course, for work done is in terms of joules. Okay, Q is the charge. So potential difference is equal to W divided by Q. Okay, the third one will be the EMF, and EMF only refers to the battery. So of course, the potential difference and EMF have the same units, which is volts. Okay, what is EMF? EMF is the amount of non-electrical energy converted to electrical energy per unit charge supply, or maybe to drive one coulomb of charge around the circuit. And the formula is the same as your potential difference, which is EMF equal to W divided by Q. But just take note that for the W wise in this case, so what is the difference between this W and EMF W? For EMF W, this EMF W is from non-electrical energy to electrical energy. So for example, for battery, chemical potential energy is converted to electrical energy. So that's the meaning of your EMF. Divide by Q, which is the charge in coulomb, SI unit. Okay, the fourth will be your resistance. So resistance, of course, is the ratio of potential difference across a resistor and current that flows through the resistor. So this formula is very important, because for this formula, right, is the formula that we will always use in DC circuit to solve a circuit problem. So R equal to V over I. Of course, there are two types of if let's just say I want to plot a graph, so resistance equal to V over I, right? So the graph will look something like this. So VI. So this graph will always pass through the origin, and of course it's a straight line. So this is the most common type of graph that we will see, and of course the gradient will represent your resistance. But for O-level wise, the graph that we will normally be given in the question is IV graph. So I against V graph. So I against V is the same thing, it's a straight line that passes through the origin. But of course, for the first graph that you see, V against I, right, the gradient represents resistance. But for the second graph, I against V, the gradient represents 1 over R. So you need to know what does the gradient represents, right? So these two graphs represents a fixed resistor that obeys your Ohm's law. All right. Whereas there's a non-ohmic conductor that we learn in COE also, which is light bulb. For example, right? Okay, I draw a VI graph. Okay, and this origin will, this graph will also pass through the origin, but the graph will not be straight. Because non-ohmic conductor doesn't obey the Ohm's law, right? So of course, the graph will look something like this. So at the very start, you obey the Ohm's law, then after that, you curve. Okay, yeah. So this very first part is straight line, but this very first, the last part is your curve. Okay, so what does you can see that the gradient, right, increases. So at the very start, the yellow shaded region, maybe I just draw a better line. Okay, so I draw a straight line first. Okay, so at the very start, it obeys Ohm's law. So it means that the resistance is the same, right? So that's why the gradient is constant. But over time, when the current keeps on flowing, right, the temperature increases. So when temperature increases, of course, the particles in the tungsten filament will vibrate more and more vigorously, and this will cause the current to, to prevent the current from flowing through easily, right? So this will actually increase the resistance, and hence the thing will curve like this, right? So this is your non-ohmic conductor. For non-ohmic conductor wise, the most common type of electrical appliance is your light bulb. Always think of your light bulb, right? Then of course I will give you the IV graph, which is this. Okay, so IV graph, you just need to think of terminal velocity. We learn in kinematics or forces, right, that when we plot the velocity time graph, the terminal velocity will look something like this. Okay, something like this. Why is the curve different? For this IV graph, because the gradient represents the reciprocal of your resistance, right? Hence, your resistance increase, right, means that your gradient must decrease. So that is the reason why your curve looks something like a terminal velocity graph. Right? So yeah, so that is something for you to take note of. Okay, so the last part will be power. So power is something that you will learn in the chapter of practical electricity. So okay, so power is just the rate of work done, or the rate of energy supplied. So there are three particular equations, which is P equal to VI. Second is your P equal to I square R. And third will be your P equal to V square R. So these are the three equations that you must memorize by heart. So when do I use P equal to VI? When do I use P equal to I square R? And when do I use P equal to V square R? Really depends on what situation you are given. Alright, so for example, let's just say you have something like this, a light bulb, and I give you the two quantity, which is, for example, 2 ampere here. Okay, then I give you the potential difference, which is 2 volts. So in this case, of course, I simply just use VI. Okay, that is the very first case. Okay, second case will be, if let's just say I give you, instead of giving you voltage, right, or potential difference, I give you current. And I give you something like your resistance, right? So resistance of light bulb, maybe I just put 2 ohms. So in this case, I simply just use P equal to I square R. After that, the last case, right? So last case, I will give you this. Instead of giving you current, I give you the potential difference now. Maybe 2 volts here. And I give you the resistance of light bulb, which I also give you in terms of 2 ohms. Yeah. So in this case, I will simply just use V squared over R. Alright, so that is the usage of your power. So power, just remember, what does power means? Power means, okay, for example, let's just say I talk about the first case, P equal to VI. 2 times 2 equal to 4 watts. So the SI unit for power is watts. So what does watt mean? Watt means 4 watts means I use 4 joules of electrical energy in 1 second. So that is the meaning of power. Alright, so that is the very quick summary of your COE.